All right, section 6.3, we had taken a look last time at some multiplication portions of this section. And today we're going to look at division. We're also going to take a look at some exponent properties, which is related to multiplication. But the division is what's coming first. So, division of rational numbers. So if A over B, if A over B and C over D are rational numbers, and we divide them, A over B divided by C over D, then this is the unique number E over F, if and only if E over F is the unique rational number, such that C over D times E over F is A over B. That might not be what you anticipated this to say. The anticipated one here will come in a minute. But this is what we mean when we do division. In fact, we do it with whole numbers very clearly when kids are learning their multiplication tables. And so they'll do something like this. They'll say, okay, well, what is 6 divided by 3? And we'll say, well, hey, it's 2. Why? Well, it's 2 because if I were to take 2 and I were to multiply it by 3, I would get back to the 6. Okay? So it's sort of the missing piece in this factor family that we're looking for, right? This 2 is the number that we multiply 3 by to get back to 6. And that's what this definition is saying. That over here, that this special E over F is what I would have to multiply the C over D by to get back to A over B. And that's what it is. So that's all well and good in terms of a definition, but it doesn't actually talk about how we go about doing what it is we're being asked to do with the division, because it doesn't work quite like multiplication. With multiplication, you can just multiply across the top, multiply across the bottom. Division doesn't work that way unless it's just really nice numbers. If there's really nice numbers, you can actually divide across the top, divide across the bottom. But that's often not what's happening with division. And so we're going to look at a division algorithm that we actually have seen and possibly what you expected this to look like when I mentioned, hey, here's the definition for division. It says the following: if A over B and C over D are rational numbers and C over D is not 0, then when we take A over B and we divide it by C over D, it's the same as multiplying by the reciprocal, which is D over C. Does that sound familiar? Multiplying by reciprocals? That is how we usually think of division. Is we don't. We just turn it into multiplication. Right? If we just flip it into multiplication, we don't even have to worry about anything else division-wise because we already established what we do with multiplication. So that all sounds really good, but there's got to be a reason why that works beyond just that's really convenient. We can ignore division and turn it into multiplication and be done with it. So I want to show you why. So I don't show why on everything we do throughout this semester, but I try to sort of sprinkle it in. And the real reason why I feel like we should sprinkle it in is because you are going to have those students who are going to say, why, Miss Long? And you're going to be like, right? You've had those kids in class where they want to know why. And they're not being annoying. They really want to know why. Like, they're not just trying to stump you sometimes. So having at least the ability to say, I'll get back to you, Joey, and you can be able to search for it and find out the why is a good thing to do. So we're going to sprinkle that in here and there. And so this is one of those places where it's really nice to be able to see why it's happening. And so I want to show you. So this says that we have A over B and it's divided by C over D. That's how it starts, right? And what I'd like to do is I'd like to write this in sort of a fractional perspective. I realize A over B is already in fractions, but I want to write it as division like this. So one big fraction inside of, two small fractions inside of one big fraction. Okay, is that step okay? Right, that's what that division back fraction bar means. It means the same thing as division. Right? It is a division bar. But it's not real nice to see a fraction over a fraction. In fact, we have a name for it. They're called complex fractions. Right? That's the name when this happens. And so we would like that C over D to not be in the denominator. And the way that we get that to happen is we want that C over D to be multiplied by D over C. Well, why would we want to do that? Well, we want to do that because if I have CD over CD, what's it going to equal? It's going to equal 1, right? So by doing this, I will end up getting a big denominator of 1. But if I do something to the denominator of a fraction, I must also do it to the numerator of the fraction. I wrote that upside down. Ignore that. Let me fix it. There we go. So if I multiply by D over C on bottom, I have to multiply by D over C on top. And now we have A over B times the D over C. And of course, division by 1 doesn't change things. So this is A over B times D over C, which is where we ended up here. Okay? So if you were doing this in a classroom, you might not use A's and B's and C's and D's. You might actually use actual numbers in here. That might make more sense to a child, right? Use 3 over 4 and 7 over 2 or whatever. I don't know. And you can do the same thing. You can just flip them and show how that works with actual numbers involved instead. All right, so let's take a look at some examples of division, because division feels somewhat different when we're working with fractions than it does when we're working with whole numbers. So let's take a step back and look at what it means with whole numbers. If we would like to do 6 divided by 2, there are 2 completely different pictures that we could do to represent that. And I want to show you what they are and show you that they are actually different, because we don't always think of them as being different. But one is helpful when we move into fractions and the other one's just not. Okay? So we're going to draw 6 items. And because I'm going to draw the picture twice, I'm just going to go ahead and draw them now, so they're all together. All right, so there's 6 items there. And there's 2 ways to divide by 2. One option is to take my 6 items and to separate them into 2 groups. So this option says I have 6 items and I make 2 groups. And what we say in the end is that each group has size 3, right? So 6 divided by 2 is 3. I had 2 groups. Now I have size 3. Okay, is that okay? That's usually sort of our default picture in mind when we think about doing division like that. But the second way is the way that's more helpful for what we're about to moving into. Instead of saying, I have 6 and I'm going to divide them into 2 groups, I'm going to say, I'm going to have 6 and I'm going to make groups of size 2. Right, I'm going to pair these are cookies. I'm going to pair up my cookies. Okay, so I'd make a group of 2. I make this group of 2. And I make this group of 2. So in this structure, I say I have 6 divided by groups of 2. And what happens is that the number of my groups, which is 3, is the answer that comes out. So the answer is not how many are in each group, right? The answer is how many groups do I have at the end. Okay, everybody okay with those 2 imageries? Okay, so here's what happens when we're looking at division by a fraction now. Now we're talking about 6 divided by 1/2. Well, let's get our 6 on here again. If I were looking at option number 1, which says I need to divide it into 2 groups, I would be asking you to divide this into 1/2 groups. What would that mean? What would a 1/2 group mean? Do you see my problem? But if we look at it in the way that the second one creates instead, I have 6 cookies and I want to divide them into groups of size 1/2. What could I do? What would a group of size 1/2 look like? Think big cookies like McAllister's or City Bites. What would you do? You'd cut them in half. Exactly. So if I wanted to, I would cut each of my cookies in halves. You've been at places where they've done this before with the large cookies, right? If you do some of the other ones, they might cut them into fourths. That's what we do with our crumble cookies and our dirty dough cookies. Cut them into fourths so that some child's not eating an entire one and making themselves sick. Okay, so this is cut into halves. So this is 6 groups. I didn't say that right. 6 cookies. So I just had 6. And then I'm going to do size 1/2. That's what I want, right? Size 1/2. And how many do I have when I'm done? 12. There are 12 halves, right? We have 12 halves. So if I take 6 and then divide it by 1/2, right? I'm splitting them into size 1/2. I end up with 12 when I am done. And that makes sense because a minute ago we had talked about the fact that 6 divided by 1/2 should be the same as 6 times the reciprocal 2 over 1, which gives me 12. So this would be an example validating that that division turning into multiplication of the reciprocal makes sense. Okay, so that's kind of all we're going to talk about in terms of division, and now we're going to turn our attention to a specific issue that's actually going back to being related to mostly multiplication. It has some division in it as well, but we're going to take a look at exponents. Now, if you have had number theory, we talk a little bit about exponents in chapter 3. If you haven't, it's fine. You've seen exponents since pre-algebra. I know my kids have seen them in pre-algebra, and then they see them again in algebra, and you see them again in algebra 2, and you see them again. You see them everywhere. So you've seen these many times over. So first, a definition to remind you what it means to have an exponent. For a rational number a and a natural number n, a to the power of n is a multiplied together n times. So if it said a to the 7th, you'd have 7 a's all multiplied together. Okay, so we're going to take a look then at some theorems of exponents. These theorems, the first thing we're going to do is just establish what they are, and then I'm going to justify why they work, okay? Once again, one of those places of, this is a really nice place to show what's going on there, and it's really fast. It's really easy to come up with a justification for the why. So the first one, when you have a to the m times a to the n, do you remember what you do with the exponents? You add them. This is a to the m plus n. The second one, when you divide a to the m divided by a to the m, this is a to the m minus n. So if multiplication turns into addition, division turns into subtraction, seems only fair. Okay? All right. Now, 3 is different than 1. What do you notice is different between 3 and 1? I don't have the base written twice, right? I don't have 2 a's written down. I don't have a written twice. You might also notice there's parentheses, right? I didn't have parentheses in the first one. So this is really a power raised to a power. And in this case, we actually multiply the powers together. So when there's not a double base written down like there was in number 1, we multiply the bases together like we do in number 3. 4 and 5 and 6, actually, all of them have kind of a distributive property feel to them. So when you have ab to the m, this is the same as a to the m, b to the m. When you have a over b to the m, it's a to the m over b to the m. And then when you have the negative, what happens is that not only do we distribute the m through, but we also flip it upside down. A negative exponent flips things. So in a very real sense, I'll do this in 2 steps. It flips it to the power of m, and then it distributes it through. Okay, is that all right? Okay, now we're going to talk about why on each one of them. So the first thing I'm going to write down is just the rule again. So if you haven't quite written them all in, if I went too fast for you, you're going to have another opportunity because these slides are going to match. So we said that this should look like this. This is property or rule number 1. And I'm going to show you by way of example for the most part, not really like a formalized proof, mostly because it's just not necessary to justify it. Our goal is really to justify why this is happening, right? Develop some sort of intuition of, oh, that makes sense. And if I forgot which one it was, I could recreate this. It's not very hard to see which one it should be. For example, the difference between 1 and 3 is, do I add or do I multiply? And sometimes people forget. Well, you shouldn't just have to necessarily remember, and you really shouldn't even have to have a note card to try and remember. It should be something that you should be able to figure out pretty quickly if you forgot. So I want to show you how you could do that. So what we're going to do is we're going to create some small numbers. We're going to do a to the 3rd and a squared. So they're just small. So the definition of a to the 3rd is that it's a multiplied 3 times. And the definition of a squared is it's a multiplied 2 times. And if you take a look, how many a's does this give you? 5. And how do we get from 3 and 2 to 5? We add. Right? it's a very direct way of proving, right, at least in our minds, justifying, well, why isn't this multiplication? Well, I can do an example of one really small and I can see it work out for me. You have to be a little careful if you use twos. If you said a squared, you're not going to be able to tell because 2 times 2 and 2 plus 2 are the same. So don't go duplicating things or using things that are having ones or zeros in them. Those don't often end up being good justification kind of examples. Okay, the next one was supposed to be subtraction. Okay, so again, we're going to use these small numbers. I'm going to use a to the 4 on top and a to the 1 on bottom. Okay, so again, definitionally, a to the 4th means 4 a's. A to the 1st means 1a. What do you do from a fraction sense when you have a times a times a times a over a? You mark them out, right? What we're really doing is we're like reducing, right? And that's how we had described it before. We're dividing by a on the top and dividing by a on the bottom. But visually, it looks like we're just marking them out. How many a's does that leave me with? 3. And how do we get from 4 and 1 to 3? Subtract, right? Yeah, so we can see the subtraction happening there. Again, if you used 4 on top and 2 on bottom, it's going to be hard to see because 4 minus 2 and 4 divided by 2 are the same thing. So you want to be a little bit careful on choosing values for it to justify. All right, the next one, 3, is supposed to be multiplication of m times n. So we're going to go with a to the 3rd. We'll do 3rd squared just because we had 3 and 2 before. Okay, so a to the 3rd means that I have 3 a's. And squaring that means I have the 3 a's twice. How many a's does that give me? 6. And how do I get from 3 and 2 to 6? I multiply, right? Okay, are these pretty okay? Seeming to make sense? Good deal. The next one, I said that we were going to distribute a to the m, b to the m. And we'll do that with 3's. So a to the ab to the 3rd should be ab times ab times ab. That's what it means, right? It have ab written 3 times. But I'm actually allowed to regroup, and I'm going to put my a's at the front and my b's at the back. And we've seen the properties that allow this to happen. They're the commutative property and the associative property. So commutative is the property that allows us to flip values around so the b's and the a's can switch spots. The associative property is the one that allows us to regroup the things into different groups that are more helpful. And so I can regroup it like this, and I can having moved them all around. And this is a to the 3rd, b to the 3rd. And you can see that 3 distributing over to the a and the b individually. Okay, next one, a over b to the m. So same thing, this one's actually easier to show than the last one. So this is to the power m. So we'll do the same 3 that I did a minute ago. So this means I have a over b times a over b times a over b. So what that means is that I multiply across the top and I multiply across the bottom. No regrouping or any of that even necessary on that. And we see I have 3 a's on top over 3 b's on bottom. A to the 3rd over b to the 3rd. Okay, the last one of these 6 has that negative exponent, so it flips it upside down, b over a. In fact, I'll just write the ending result. The b over the a, and it distributes the m through. It's now a positive m because I flipped it. So we have a to the m over b to the m. And move that down just a little bit. Let's just do this with negative 2. So what I'd like to do is I'd like to separate the negative 2 into the 2 things that make negative 2 up. In particular, that would be the 2 and the negative 1 power. So 2 and negative 1, that's just breaking apart the number negative 2. So from the last property that I just did, I know I can distribute the 2 across, right? A squared over b squared. And the meaning of a negative exponent is that it's reciprocal. Like that's what it means. So when we take a look at this, we get to flip this upside down. So the b squared on bottom is now on top, and the a squared on top is now on bottom. Now there are a couple other properties as well. I believe those are next. Yep, additional exponential facts that we will utilize. It talks about what a to the 0 is. What is a to the 0? Do you remember? It's 1. So it means the a has to be not 0 to start with, but anything to the 0 power except 0 itself is 1. So 5 to the 0 is 1. 3/4 to the 0 is 1. All those, okay? And then on the bottom, 8. 8 is a special case of number 6. It's actually just 1 over a to the n. And on this one, I can actually show you a very nice, simple, like legit proof of why that works, and then I'll do an example on the other one. So we're going to take the a to the 0, and we're going to rewrite it in a funny way. I'm going to write it as a to the m minus m. Actually, let me put it as a to the 0 at the beginning first. Now, you might look at that and say, that was super strange. Why'd you do that? But regardless, can you see why it's true? Right? 0 is the same as m minus m. You could use numbers if you wanted. 0 is the same as 5 minus 5, okay? And if I use property number 2 in reverse, so property number 2 said that I can subtract exponents. And the location from which those exponents came when I subtracted them was that one of them was on top and one of them was on bottom. So I'm using the property number 2 sort of backwards of how we normally use it. But what is the value I get when I have the same thing on the top and the bottom of a fraction? It's 1, right? 7 over 7 is 1. 342 over 342 is 1. A to the m over a to the m is also 1. And you can see, so this is a series of equal statements, that a to the 0 over here is then equal to 1 because each step was equal to the next one. And again, you can use numbers if you'd like. And then the last one we'll do an example for is a to the negative 3. And so we talked about the fact that we can separate these out. So we'll do a separation like this. I separated it the other way last time, so I'm going to separate this way this time. So negative 3 is negative 1 and 3. So we put the negative 1 in one place, the 3 in the other place. So a to the negative 1 is 1 over a, because that's what it means. It's the reciprocal. And then I have the power of 3. So we're going to do this to each per term, right? It's going to be a distribution kind of property. 1 cubed over a cubed. And what is 1 cubed? 1. Yeah. So you can see that I end up with the a cubed in the denominator, which is exactly what it said I should do if I have this over here starting out like that, right? Okay, all that to say, am I going to ask you to show that on the test? No, right? This is not all about teaching to a test. That's not the point. You guys are going to teach people someday, and you may not think you're going to teach this, and you may not, but some of you will. And some of you are going to have that student Joey, and Joey's going to want to know why. And even if you can't think of why in the heat of the moment, you at least be like, okay, I may not know why, but I can figure out why for Joey, and I can come back and I can give myself some credibility with Joey, because you're not going to have any credibility if all you can say is because I said so, right? Or because the book did it that way. That's even worse, okay? Being able to come back with a reason why is really important. So I want you to see some of those reasons why. Here's what we're going to do with them, however, is we're going to use those properties and we're going to actually manipulate expressions and simplify them, okay? So there's often more than one way to do these problems, and that's fine if you're doing it a different way, because if you've done them in a correct way, even if it's a different way, you're still going to get the same answer. So one of the ways to do this particular one is to notice I have a to some power on top and I have a to a power on bottom. So it looks a lot like property number 2. So I can actually write the top exponent, which is a 1, and then I can subtract the bottom exponent, which is minus negative 3. Again, not the only way to do this, but it is a way to do this. I can do the same thing with b because I have a b on top and a b on bottom. The exponent on the b on top is on the top is a 4, and on the bottom it's a 2. So it's 4 minus 2. What happens when I have 1 minus negative 3. You change it to addition, and what will that give you? 4. Okay, good. Now the next one, you know what, I have more space over here. I'm going to move it over here. The next one says b to the 4 minus 2. So what's 4 minus 2? 2. So I have b squared. Okay, it's not the only way to do it. Some of you were looking at that and you were like, negative exponent, I would have done this. Okay, one option is you could put the negative exponent and pull it to the top and make it positive. That's another way of doing this one and thinking about it. It'll work. You probably never thought about it, but the reality is exponent rules are easier to do with variables than they are with numbers. A lot of times we somehow think that numbers are sort of better or more helpful, but they're not always. And the reason that B sort of has this issue is that the pieces inside the parentheses don't match. And all of our properties, we're hinging upon the bases matching. The A's match each other, the B's match each other. This doesn't do that. So somehow I have to change this expression so that they do have the same matching pieces. So there's more than one way to do it, but one of the ways to do that, 2 and 5 don't factor or reduce any, but 4 and 25 do. So how can I factor the number 4? Okay, so I'm going to write it actually as 2 times 2. Is that all right? Okay, so 4 is 2 times 2. What about 25? It's 5 times 5. Okay, is everybody good so far? Okay. Now, that's not the only way to write that. In fact, it would be a little cleaner if I wrote it as 2 over 5, and then I squared it. Because 2 times 2 is 2 squared, 5 times 5 is 5 squared. I still have all of that raised to the negative 6th power. Now, notice the second piece. Oh, I left the 3 off. Sorry about that. Notice the second piece over here. I have a parenthesis inside of a parenthesis, right? That's property 3. What do I do with my exponents when I have a parenthesis inside of a parenthesis? I multiply. So that first piece is going to stay the same, 2 over 5 cubed. But now I'm going to have 2 over 5, and I'm going to multiply the exponents to give me a negative 12. Right? 2 times negative 6 is negative 12. Not adding, multiplying. Now, this still isn't like beautiful or anything, but the bases match, right? 2 over 5 matches the 2 over 5. So this actually puts me back in case number 1. In case number 1, I had a base and another base, they matched. And what did I do with their exponents? I added them. So we're going to add those exponents together. So I still have 2 over 5. What is 3 plus negative 12? Negative 9. Thank you. Now, there's a couple of things we can do. One thing we need to do for sure is that we need to recognize that we're not going to leave things with negative exponents. Okay? So we are going to use one of those properties that talks about negative exponents. The one that's most clearly like this one is property 6. Property 6 says, what if I have a fraction and it has a negative exponent? And it says, hey, you can flip the fraction upside down and you can put the numbers on each of them individually. So I'll take that in 2 steps. First, let me turn the fraction upside down, which makes the exponent positive. And then I'm going to put the exponent on each of the pieces that I have. So this is 5 to the 9 over 2 to the 9. Now here's the deal, folks. I do not want you to figure out what is 5 to the 9 and 2 to the 9. It is the height of unhelpful, okay? This is a very concise, clean, compact way of writing it, and that's where we leave it. Okay. Example 7. We're going to use properties of exponents now in order to solve for those exponents, or at least some portion of those exponents. So looking at the left-hand side, what property of exponents, 1 through 8, do you see that we could use? Flip back if you need to look at the numbers or whichever one, whatever is it. What is it? It's property number 1, okay? Property number 1. And property number 1 said I can add the exponents, so it's n plus 7. Now, we're not interested in getting too awfully messy here. So these numbers you're going to be working with are going to be nice numbers. 64 is a very nice number. If it's not a number if you didn't know it was nice, you're about to find out why. We're just going to factor 64. So what will 64 factor into? All right, nobody's talking. I'm going to go with 8 and 8. How's that sound? Okay, fantastic. How will 8 factor? 2 and 4, wonderful. And I'm going to do that twice, right? And 2's are prime, so I'm going to stop at the end of the 2's. And how do 4's factor? 2 and 2. So this is a lovely number because it's all 2's. And the reason that 2's are very lovely here is because what's on the left-hand side? A 2. Yeah. How many 2's did I get? 6. There's 6 of them. So I'm going to be able to write the right-hand side as 2 to the 6th. Now, I'm not done, but I'm running into things. So you know what? Let's do it this way. Make this a little bit smaller so I'm not running into things quite as bad. At this point, if you notice or know what you want your exponent to be, that n to be, you can just tell me n is equal to this. What would n have to be so that n plus 7 is the same as the exponent 6 on the other side? It'd have to be negative 1. So if you can just see that, then that is fantastic. Write down n equal to 1 and you're done. If you're like, what did she just do? You can actually show it. N plus 7 is supposed to equal the 6. And then you can subtract the 7 from both sides. And you will get n equal to negative 1. So show it if you need to show it. Don't show it if you don't. It doesn't matter to me. Either of those are fine. Now, it works for inequalities too. So on the left-hand side, it's already in this very compact, nice form, 3 to the n. But the right-hand side has this unhelpful at the moment, number 81, and it's in the denominator, which we can fix as well. But how does 81 factor? 9 and 9. How does 9 factor? 3 and 3. So 81 is how many 3's? 4. So notice what I have here. I have 3 to the 4th, but it's in the denominator. Now I want to compare them, but I don't want it in the denominator. I want it to kind of move its way on up, right? How do I get it to move from the denominator to the numerator? Well, that's property number 8 in reverse. I can pull the 3 up to the numerator if the exponent's negative. That's property 8, but it's moving property 8 the opposite direction of how it's stated, which is allowed, just not always intuitive. So what can I say about my exponents now? They need to be the same, but not exactly the same. There's a symbol in between that doesn't say equals this time, right? There's a less than or equal to sign. So my exponent n would have to be less than or equal to the 4. Okay, the less than or equal to stays the same because that's the way the question began. That's the way the answer will be as well. Okay, approximation. Approximation is a really good thing to be able to do because a lot of times you don't need a calculator to find an exact value. You just want to make sure that when you get to the register, you're going to have enough cash in your pocket, right? So you're approximating along the way before you get there. Well, this is one of those kind of things. What is 20 and 1/3 divided by 9 and 7/8 approximately? Well, we can estimate. We did this with some of our fractions back in section 6.1. 20 and 1/3 is about what? Think nice number. 20. It's about 20. I mean, it's a little more than, but let's be real. It's not much more. 9 and 7/8 is about what? It's about 10. So what is 20 divided by 10? 2. So this is approximately going to be the number 2. Why does it matter? Well, because if you're doing the problem out longhand and you want to sort of check that it makes sense and you're getting a number that's like 20 something, you'll know it doesn't make sense because it should be about 2, not about 20. You're off by a decimal somewhere along the way or by a place value. All right, Jasmine. Jasmine is reading a book. She has 1/4 of the book left and has read 246 pages. How many pages does she have left? All right. So there's several ways to do this particular problem. We'll encounter something in 6.4 that's actually another option as well. But one thing that it would be good to notice is that it tells you how much of the book she has left, but it also tells you the number of pages she's already read. Do you see that? Those are not the same quantity. One's saying what's left, the other one's saying what's finished, right? What's finished and what's yet to be finished. Those are different quantities. But if she has 1/4 of the book left, right? How much has she read? 3/4. So if it's 1/4 left, then there's 3/4 finished. Okay, does that make sense to everyone? Okay, that 3/4 now is in direct relationship to the page numbers. 3/4 of the book is the 246 pages. What is it that we don't know?
How many she has to read?
Yes, something else. Because we're looking for how many she has left to read. That's true. We don't know the total number in the book, right? So we need to know how much she has left to read. And if we knew how many pages were in the book, then we'd be able to do that, right? So we're going to let X be the total pages in the book. All right. So 3/4 of the total pages in the book is going to equal the 246 pages that she has read, because she's read 3/4 and she's read 246 pages. How can I solve this equation for X? Okay, I think you mean multiply. Yep, okay. So we're going to divide by 3/4, but that's the same as multiplying both sides by the reciprocal. So on the left, we get X, which was the goal. On the right. So what is 246 times 4/3? If you want to grab a calculator real quick, please do so. $328. So this is 328 pages, right? Well, we've got X, what X equals, but we want to make sure that we're answering the question that's asked. What question is actually asked here? How many pages she has left? Does she have 328 pages left? No. How can we find out how many pages she has left? Subtract. We can take 328 and we can subtract 246. Now, it's probably worth noting there's another way to do that. Does anybody know what it would be? I don't think it's the way you would do it, but you could also take the 328 and multiply by 1/4. 1/4 of the 328 is also going to be 82 pages. Either of those will give us 82 pages. Okay, we have one more question in this section, and it's a clever one. Are you ready for it? We have some very generous children who are going to share some marbles. Al gives half his marbles to Jose. Jose gives half his marbles to Isabel. Isabel gives half her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al have now? Okay, this repetitive process of giving the marbles away is actually what puts it in this exponential category, by the way. So, what could I do? Working backwards is a good option. Let's actually write down all the people's names kind of in order so that we can get the working backwards to be useful to us. We have Al, and then we have Jose. And then we have Isabel, and then Letitia. All right. So Letitia, presumably, because the description sort of indicates that, didn't start out with any marbles. But how many does she have now? She has 4. So let's look at this as what she has. You know what? Let's do it this way. What she started with and what she has now. She started with 0 and she has 4 now. Okay, where did her 4 marbles come from? From Isabel. Isabel gave her the 4 marbles, right? So Isabel gave half her marbles away to Letitia. So how many does she still have now? She has 4, right? She gave away half. So she kept half, she gave away half. She has 4. But how many did she start with? She started with 8. But where did Isabel get her marbles? She got them from Jose. So how many marbles does Jose have now? 8, because he gave half of them away, right? So Jose has 8 now, but he started with 16. Where did Jose get his marbles? Al. So how many marbles does Al have now? 16. How many did he start with? 32. So here's my chart. It identifies lots of things, but we want to make sure that we answer the question asked, which is how many marbles does Al have now? And that answer is 16. And anytime we do application problems or word problems, we need to write down what we have. This is 16 marbles, right? Not just 16. We're answering with units. The units here are marbles.